Hey everybody, it's Coach Stoltenberg again, coming to you with the next video on the reactivity unit, dealing with acids and bases. Today we're going to talk about how to actually calculate pH, pOH, and things like that. But before we do, just want to touch on one little thing here, dealing with strong acids and strong bases, and then we'll get into the pH and pOH. So here we go. Strong acids are acids that completely dissociate. Completely dissociate simply means that when dissolved in water, it completely breaks into its ions. We know that when we're dealing with acids, the cation is always hydrogen. That's what makes it an acid. Well, strong acids are compounds that when they dissolve, they completely break down and release all of their H plus ions into that solution. This does not mean they have a high pH or a low pH. It does nothing to do with pH. Whether an acid is being considered a strong acid or a base is considered a strong base has nothing to do with pH. It only has to do with how much of that compound dissociates. This is a common misconception. People think that something with a low pH, like a pH of 1, is a strong acid. No, it just means it's a concentrated acid. Whether or not it's a strong acid depends on whether it completely dissociates. When it completely dissociates, it means it forms lots of ions in water. Well, lots of ions in water means they're strong electrolytes. Yeah, so a Gatorade could be putting acid in your water and call it an electrolyte because it technically is. Just think about that. They don't, so don't start freaking out. But there are 6 acids that we consider strong. I don't expect you to know this. You don't have to memorize this list or anything. Just the main point here is strong acids make good electrolytes, which means they're good conductors of electricity, but it has nothing to do with pH. Nothing to do with pH. pH is about the concentration, how much H plus, how concentrated the acid is, not the kind of acid. The kind of acid determines whether it's strong or weak. At the same time we have strong acids, we also have strong bases, and it's for the same reason. They completely dissociate in water, meaning they produce more ions in water than weak bases. They more completely break apart. Again, that makes them strong electrolytes or good conductors. This is your list. Generally, group 1 and 2 metals are considered strong bases. Lithium hydroxide, sodium hydroxide. Any group 1 or 2 hydroxides, generally speaking, are considered strong bases. Again, you're not going to have to distinguish from a strong base from a weak base. Just to understand what it means to be a strong acid or base, the fact that it makes them good electrolytes, good conductors, and that it has nothing to do with the pH. All right, moving on. Water equilibrium. All right, before we get into this, just understand that we're about to talk about a bunch of math that honestly, like how they came up with these numbers, it's just one of those things that it's like really complicated and kind of above my ability to understand. Because we start talking about logarithms and things like that. So if you want to try to figure it out, awesome. But just know you don't really have to. We just really need to know these equations, and we'll get to those equations here in a second. But I'll do my best to try to explain it. If you get a little lost in here, don't feel too terrible about it. So again, we talked about this earlier. Water molecules can function as both an acid and a base, making it amphoteric. What's interesting is that not only can it act as both an acid and a base, like when it's reacting with things, but it's also acting as an acid and a base constantly. In a sample of pure water, what actually you have happening is one water molecule will act as a base, meaning it will accept a hydrogen from a second water molecule, which means it is acting as an acid. This reaction happens, and it is constantly happening in every sample of pure water. However, as soon as this happens, the hydronium ion is formed, H3O plus, and the hydroxide ion is formed, OH negative. And these two are very strong acid, very strong base, and just as fast as they are formed, they react with each other to immediately turn back into water. So what this means is that at any one time, in any sample of water, not only do you have H2O, but you also have H3O plus and OH negative. So at any one time, water is not only considered neutral, but it also has aspects of an acid and aspects of a base. At all times, water can be called an acid and a base. Well, it has aspects of both. Here's the reaction. Two water molecules react. One acts as the proton acceptor, one acts as the proton donor. We get the hydronium ion formed and the hydroxide ion formed. This water molecule is acting as the as the base. This water molecule is acting as the acid. You get the hydronium ion and hydroxide ion formed. But again, these two are so strong and so reactive, this reaction almost immediately, pretty much immediately takes place in the opposite direction. But what you have to try to wrap your mind around is that it's constantly happening in both directions. So at all times, in any sample of water, you'll see all three of these things. Most of it is water molecules, but there is a very small percentage of hydronium ion, and there's a very small percentage of hydroxide ion also within that sample. All right, here's where the math comes in, and here's where it gets kind of fuzzy. Again, I'm not going to try to explain how this number was can't come up with, but there's some mathematical principles behind it. If you really want to look it up, look it up. But what we're talking about is a water equilibrium constant, and what we really need to know and understand is that this right here, this part of it right here, is what is important to us. Basically, what the water equilibrium constant says is that if you take the concentration of H plus and you multiply it by the concentration of hydroxide, in every solution, in every sample of water, every solution that's created, if you take these two things and multiply them by each other, you should always get 1 times 10 to the negative 14th. In water solutions, pure water solutions, or pure water, generally speaking, these two things are equal. If it's neutral, these two things are equal. H plus concentration is equal to hydroxide concentration. So if this statement is true, then each one must be 1 times 10 to the negative 7 in neutral solutions. Well, we know this isn't always the case. It's not always neutral. So, once you start influencing that solution, changing the concentrations of H plus and hydroxide, now you're going to tilt that solution one direction or the other. If the H plus concentration is greater than hydroxide, it's acidic. If the hydroxide concentration is greater than H plus, it's basic. This equation right here, this number, is basically where the pH scale comes from. The reason why the pH scale runs from 0 to 14 is because of this number, and I'll show you what I'm talking about here in a little bit. Again, this is dealing with logarithms, so the math behind it is pretty complicated, but luckily for us, we have these little nice invention called calculators that will do a lot of the work for us. So how can we use this number to calculate pH and pOH? Well, that's what we're going to look at next. Scale for measuring the H plus concentration is a huge range, extremely large. It goes from really concentrated to not very concentrated at all. So we need a large scale. That's why the logarithms are used. And it covers base 10, so it's factors of 10. So pH of 1 has a concentration of 0.1 moles of H plus per liter. So 1 molar H plus. pH of 3 would be a solution that's 0.001 per mole per liter. pH of 7 is, obviously that many factors of 10 less. What this means for y'all, it just means this right here. This is the equation. This is how we solve for pH, where we take the negative log of the H plus concentration. This is the equation that we're going to use quite often here in the next couple of days practicing these calculations. Well, you know how math is, and you know how algebra works, and you know that if you can write an equation one way, then you can rewrite it in another way to solve for a different portion of that equation. So while we can use this to solve for pH, we can also use it to solve for H plus concentration. So we can rearrange this equation to make it this. So if we want to solve for H plus or hydronium ion concentration, we simply rearrange the equation and it's 10 to the negative pH. So these two equations are the ones we're going to use for dealing with pH or H plus. Well, if you remember from last video, I said there's also another scale, right? There's a POH scale, which essentially is the opposite of the pH scale. But it basically works the same way, but instead with in reference to hydroxide concentration. So here, POH, for solving for POH, we're going to take the negative log of hydroxide. If we're solving for hydroxide concentration, we do 10 to the negative POH. Again, whether you understand what this math actually means or not, it's not really that important. As long as you know how to punch the buttons into your calculator, you'll be all right. In the end, if you have one pH or if you have POH, then you can easily find the other, because at all times pH plus POH will equal 14 at all times. So if you have like I said in the previous video, if you have a pH of 2 and you're trying to find POH, it's pretty simple. 14 minus 2 would give you a POH of 12. Same thing if you're going the other direction with that. So when we start getting into these questions, what you're solving for and the method you're going to use to solve for it depends on obviously what the question's asking and what the question's giving you. So these are the equations we'll use when we're talking about pH or H plus concentration. These are the equations we'll use if we're talking about solving for POH or hydroxide concentration. And then we have this equation in our back pocket to use to solve for one if we have the other. Now, one thing I want to talk about real quick before we move into actual calculating is different ways you're going to see this. Now, try to bear with me here as I'm kind of like free writing this. All right, so this is or. That's or. That says or, not on. This can be written another way. We can solve for pH by taking the negative log. Holy moly, I feel like there's a better way to do this. Log. Aha! Negative log of. This is hydronium, right? Well, what did we say is the same thing as hydronium? That's right. H plus. Oh, look at that. That is nice. Nice. That kind of looks like a 7, doesn't it? So depending on how the question is worded, it could say hydronium, it could say H plus. Essentially, they're saying the same thing. Well, there's another thing that the question can say, but it still be talking about the same thing. Earlier in this video, I mentioned strong acids and strong bases, and I mentioned that they're defined by the fact that they completely dissociate, meaning when they dissolve, they completely separate into their ions. Well, if you're given the concentration of a strong acid and it's dissolved in water, then you know that that concentration, all of that hydrogen concentration, is in ion form. So essentially what you can say is that the concentration of a strong acid is equivalent to the concentration of hydronium or H+. So what I'm trying to tell you in a very long-winded way is that you can also take the negative log, of the concentration of an acid. I'm sure there's probably a better way to do this, but this is fun, and I'm sure some of y'all might be laughing right now. Oh yeah, look at that. That is a nice written word right there. All right. So these are three things are all essentially solving for the same thing. They're all solving for pH. The negative log of hydronium, the negative log of H+, or the negative log of the acid. If it gives you the concentration of an acid and asks for pH, negative log, that's it. Same thing down here. POH. For solving for POH, we can take the negative log of the hydroxide concentration or the negative log of, anybody want to take a guess while I slowly write this out? I'm sure at least one or two of y'all have probably guessed that if it's a strong base, then we can also use the concentration of a base. Oh my goodness, that is awful. Sorry. All right. Yeah, that says base. That says base. Same concept though. Strong bases completely dissociate. So when you have a strong base and it completely dissociates, then whatever its concentration is, that would also be equivalent to the concentration of the hydroxide in that base. So if you're given the concentration of a base, then that is equivalent to the concentration of hydroxide. One thing you do have to pay attention here and here is how many hydrogens that's given up. If it's a single hydrogen acid, then it's straight whatever the molarity is. Or same thing here, if it's a single hydroxide base, just use whatever the molarity is. However, if it's H2SO4 or BaOH2, then you have to double that concentration, because for every molecule that's getting broken down, you're getting twice as many hydrogens or twice as many hydroxides. If we come across one of those problems, I'll go through it. All right. Let's go ahead and we'll end this video here. We'll come back in the next video and we'll start with how to actually do these calculations on the calculator. So the next video will completely be dedicated to just doing the calculations themselves. Yeah, that sounds good. All right, so I'm going to stop here and we'll see you soon. All right.